In today's video, we're going to be coding up the Particle Swarm Optimisation in MATLAB. Now, if you have not seen part 1 of this series, where we developed the optimizer functions and the optimizer ranges functions, which will both be used in this video, I highly recommend checking them out just so you understand the premise of the code and what we are trying to optimize against. So, Particle Swarm Optimisation is very similar to the BAT algorithm, which we coded up in the previous tutorial, in the sense that it mimics the movement of creatures through the search space. However, Particle Swarm Optimisation does not have the echolocation to assign random movements for bats. So in Particle Swarm we use inertial velocities and acceleration constants that are related to knowledge that the swarm currently has. So we're just going to start by clearing the workspace, and then we are going to start defining our Particle Swarm Optimisation settings. We are going to have a population size equal to 50. We will have a number of movements, again equal to 50, and we will set a dimensions variable, which we know is equal to 2 because we only have an x and a y coordinate to optimize. And we're going to start now defining our velocity coefficients. So we have a inertia coefficient, which I'm going to set to be 0.2, and we have an acceleration, which is personal, and I'm going to set that to be 0.1, and we have an acceleration social, which I'm just going to set to be 0.05. Now these numbers we will play around with later on, and I will show you exactly why I picked these relatively small values just for the initial testing. So we are now going to define our optimizer, so select the optimizer function, and we will start with the actually function, and we will use our optimizer ranges function to return our x range and our y range for the optimizer. And we will just initialize our swarm population. So in a similar way to how we coded up the initial population for the BAT algorithm, we're going to do it inside a for loop. That way we can analyze the fitness of each of the particles in the swarm as they are being initialized. So for population size, we will say that the first population value, which is the x coordinate, is going to be equal to the x range of the maximum value taken away from the minimum value as a piecewise multiplication of a random vector drawn from a normal distribution plus the minimum x range value. And we do the same thing for the y coordinate. So we say it's now the y range 2 minus the y range 1, which is then multiplied as a piecewise operation of a random vector drawn from a normal distribution, not a random distribution. And we can then say that the fitness value, the corresponding fitness value, is taken from the optimizer functions of the population of the x value, the population of the y value. We want to pass in our optimizer, and we want to set mode optimizer. So again, if you are not familiar with what is going on here, we are just using the optimizer function that we defined in the first tutorial. So again, I recommend just checking that out if you have not yet seen it. And we then end our for loop. Now we're going to define our points plotter, so we're going to say points plotter, and this is just going to allow us to visually see what is going on within our population. So we're going to say that function points is equal to population plotter of the population variable. We're going to pass in our optimizer and we're going to pass in the points variable. And we are going to say that if the points variable is empty, then we want to create our figure, clear the axes, turn the hold on, and we want to plot the optimizer function of the optimizer as a contour map. Else, so if we do have points, we will just reset the location of the points, and we will say points is equal to a scatter plot of the population of all the x values, all of the y values, and we actually need to invert these because we inverted the contour map when we created that function. We're going to set them to be black circles with a marker face color that is also black. We will apply a small pause just so we can visually see what is going on throughout the simulation, and then we'll initialize our draw now. I've called this the wrong thing, we'll call it points plotter. And now come back to our particle swarm. We will say that points is equal to points plotter, and we need to pass in our population, our optimizer, and we do not own a points variable. So if we just run this now, you can see we have the Ackley function as a contour map, and we have a swarm of 50 particles located throughout our search space. We will now define the particle best position as being equal to the population, and we will define the particle best fitness as being equal to the fitness. So as I mentioned previously, the way particle swarm works is we move with a certain velocity based on prior knowledge that each particle in the swarm has of their current best location, so the best location they have been, and also the best location of the entire swarm. So what we're just saying here is that the particle's best position is currently equal to the position they're at because they've only been in one location, and we also set the fitness, and these will be updated within our run statement. We can then define the best overall movement with the index as being the minimum of the particle best position, best fitness, and this will be the best solution that any of the particles have been at. We can now initialize the swarm dynamics, and we only have one variable here, which is going to be velocity, and we're just going to set it to be equal to a 0 array of population and dimensions. So we can now start to begin our run statement. So we're going to just call this new section run, grab some space, and we will initialize with a tick time stamping, and we will say for movement is equal to 1 to the number of movements, which we've described as being 50. And then we are going to say for each of the particle in the population, we will now update the particle dynamic. So as I mentioned previously, we update the velocity of the particle based on an inertia value, an acceleration personally, and an acceleration socially. So I'm going to define these as being 3 individual velocity vectors, which we will then summate together to get an overall velocity vector. So we're going to say that the first velocity is equal to the inertia value multiplied by the previous velocity of this particle. So the second velocity is going to be is going to use the acceleration personal multiplied by a random array which is of one to dimensions, and it is going to be multiplied as a piecewise operation as the distance between the particle best position when we evaluate it as a function of the particle subtracted by the population, so the current location of the particle. So what we are saying here is we are taking the best known position for this particle, and we are working out the difference between that location and our current location, and we are then multiplying that by our personal acceleration factor. Same thing now for the third acceleration, but this time using the social coefficient, one of dimension, as a piecewise operation, and this time we will use the best position, but rather than using the particle, we will use the index value of the best known bat. So where we calculated here the minimum value, we return the index, and we will use this corresponding position with, again, the removal of the particle current location. We can then update the velocity of the particle just simply by adding the three velocity vectors together, and update the position of our particle by just simply adding the previous location to the newly defined velocity. Now, as we did with the BAT algorithm, we need to actually apply a population scale to ensure that we do not move outside of the search space. So we're going to say population scaling, and our function will return the population where the input is the population, the x range and the y range value. And we'll just say that we will query the population when the first index of the population, so all of the x values, if they are less than x1, then we will set that value to be x1. Now we'll do the same thing for the second value. So again, if all of the x values, if any of them are greater now than x2, we'll just set them to be x2. And then we can do the same thing for all of the y values. If it's greater than y1, this we're looking now in the second array, we'll set that to be y1, and do the same thing, but this time if it's greater than y2, we set it to be y2. And this will prevent our population from moving outside of the search space. So we can now say that the population of the particle is equal to population scaling, and we will just pass in our particle population, our x range and our y range. We can now calculate the fitness, and we will say that the fitness value and the target is equal to optimizer functions, and we pass in population particle 1, population particle 2, we pass in the optimizer, and we query at mode optimizer. We can then say that the fitness of the particle is equal to the fitness value, and we will now perform a check on the fitness values, because we need to update our best positions if the fitness is improved. So we'll say if the fitness value is less than the particle best fitness for the particle, then we will say particle best position for that particle is equal to the population of the particle, and we will say the particle best fitness for the particle is equal to the fitness value. We will now say if the fitness value is less than the best, so the best we calculated initially, we will say that the best is now equal to the fitness value, and we update the index to be equal to the particle. So this will now just allow us to establish whether or not we've increased the best overall or just the best in terms of this particle. And that is it. So that is the dynamics performed, and we will just now do our update. So population is actually points plotter, and we pass in our population, we will pass in our optimizer, and we will pass in the points variable. So let's just quickly run this and see if we made no errors. So you can see that the swarm is starting to home in onto the solution, and then the simulation ends after 50 movements. So let's give ourselves an understanding of what's happened. So we'll just say t is equal to toc with a print statement that the simulation ended after a certain number of seconds with a certain number of movements. We'll give ourselves a new line character, and we'll pass in the t and the movements variables, and define our best solution as saying best solution is when x is equal to some x value and y is equal to some y value with a fitness of some fitness value with a new line space, a new line character, and then we will pass in population index 1, population index 2, and then the best, like so. You see they all home in, and the simulation ended after 1.583 seconds after 50 movements, and this was our best solution. So we know that the Ackley function has a best solution of 0 at 0, 0. So if we now start to increase some of these coefficients, so let's bring that up to 0.1, and let's bring this up to 0.2, you can see they move a lot faster, and we have converged towards the global solution. Now if we were to start with an inertia of, let's say, 1, this is what happens. They sort of are not able to converge because they have the velocity is so high that they just sort of fly around the space. I mean, it's a nice pattern, but it's not what you want. So that is the reason why I started out with quite small inertia values. So let's have a look at how changes to each of the acceleration coefficients will impact the rate of convergence or the characteristics of the convergence. So if we just look at what we've got here, we've got quite a slow convergence, and we do not reach the global solution. So let's increase the inertia, and they move a lot faster, but you can see that some of the particles are not starting to converge. Let's increase that, so I'm going to try and amplify it. So there you go, you can see this sort of the pattern of them moving. They move sort of around the global solution, and this is because they are shifting towards their personal best with the same weighting as they are to the social. So if we were to just decrease the personal, they actually home almost linearly in onto the solution with very little deviation. And this is because we want them to go towards the global solution. So if we favour the best acceleration in terms of the social aspect, so the best overall solution, we can actually increase the rate of convergence. And we can amplify this again by just setting our personal to be 0.5. And as you can see, these particles here are just favouring local minima because they are heavily weighted towards moving towards their best solution as opposed to moving towards the global solution. So I would always recommend the particle swarm having a higher social coefficient than your personal coefficient, and it increases the rate of convergence. Now you can see we converged straight onto a global solution, and it took us 50 movements before it ended. So as with the BAT algorithm, we will start to initialize an n set of conditions. So we will say 3 decimal places, and I will specify a minimum number of movements of 20. So we can say if we round the best solution to 3 decimal places, and if that is equal to the rounded of the target to 3 decimal places, we'll break the simulation. And we will say only do this if the number of movements we are on exceeds or is equal to the minimum movements. So now the simulation will end when we converge, but only once we've exceeded 20 movements. So you can see the moment we got to 20, simulation ended on 20 again. So you can see how just adjusting these inertial values and how we can weight movement towards the personal and towards the social, how it actually impacts convergence. So let's try some different optimizers. So the Beal optimizer is very tricky, and we have converged to a global solution. We've ended up with a few of the particles favouring their own locations, and you can see we've falsely converged into a local minima, not the global minima. Successful convergence, once again. So you can see we are getting quite a good rate of accuracy, but we are getting a sort of stuttered approach with a few of the particles. Let's look at the cross-train function. You can see we get very fast convergence. We actually have 4 global solutions, so we should get very quick convergence, and it's going to be random as to which one of the minima we converge towards. Let's look at the Levi function. So we instantly converge onto the global solution, and again let's look at the Goldstein price. Again, instant convergence. We had one dangling there who did not want to converge. Let's look at the egg crate. Again, instant convergence. So that sums up particle swarm optimization. If you have any questions, please leave them in the comments below. Don't forget to like and subscribe, and I'll see you in the next video.